Okay. Hi, everybody. I'm Luca Marchionni from Par Robotics. And today I'm going to talk a little bit about our company. It's the first time I have a talk here at ROSCon. It's quite exciting. And I will give you a short overview of the software development at our company. And then I will dig a little bit into some tools that we have been using that I think are quite convenient for developing robots with ROS. And then I will talk about our control architecture and more in detail about all body control. That is something that we use on our bipeds and also on Tiago robot that you could have seen at our booth. And some application of this software for the Space Robotic Challenge. We at Par Robotics started doing robots more than 10 years ago, before Willow Garage. And we got excited when we saw ROS, and we adopted ROS since the beginning almost. So in 2011, actually, RIM, the white robot with wheels, was the first robot that was for sale using ROS. And in particular, we were using the full navigation stack, move it, not yet move it, but manipulation using joint trajectory controllers, all this stuff. And then for RIM-C, we contributed to developing ROS control. So RIM-C was the first humanoid robot, biped humanoid robot with ROS control. And then recently now we have a huge family of robots, smaller one, mobile bases, mobile manipulators, Stockbot, that is for automatic inventory, a new biped that we just released last year that is fully torque controlled for industrial applications. This has been possible thanks to a lot of partners and collaborators all around the world. We ship robots everywhere, and we are involved in several European projects. So why we use ROS? It's, there can be a lot of answers to this question. The main reason is that we want to deliver robots that works, and we don't want to reinvent the wheel, okay? So in some sectors, ROS can also be considered a selling argument. And for sure, it's quite helpful to use all the powerful development tools that are available with ROS. So I'm thinking about RVs, I'm thinking about gazebo simulation, ROS control, and a lot of introspection and debugging tools. We want to focus on building complex robotics applications. So it's important to have shared effort with the community to benefit everybody from the ROS libraries and the core of what we are doing. We have some public repositories that allow the people to test our robot in simulation and test some of our libraries. So you can have a look at the GitHub repository or the wiki tutorials for getting an idea of what we are doing and which are the capabilities and the application of our robots. Soon also we will release the simulation of the new biped. As I told you before, it's a full-size, human-size biped robot with torque control in every joint, EtherCAT, and has been designed thinking about an industrial application because we have some pilot project with an aerospace manufacturer that is interested in evaluating such kind of platforms for complex tasks such as drilling or riveting in inconvenient ergonomically configuration for humans. Short overview of what we have inside our robot. We use Ubuntu. We have a real-time operative system with Xenomai or Preempt RT. We use ROCOS because we really like its component-based approach. And then we use, in the current stable version of our robot, we have ROS Indigo and PAL Dubnium, that is our software distro. We are working on migrating to Ubuntu 16, to Kinetic. Our new distro will be Erbium. And for the future, we are waiting for ROS 2 because we believe that will give us more flexibility and control over inter-process communication, deployment, and hopefully more security, because at the moment they are quite fragile, the application, because everything is let's say, open, there are no encryption in the communication, and someone publishing on TF can get your system completely stuck. One important part of our work is to validate our software on hardware, because we build hardware and we develop software, and the software without hardware validation is nothing. So every time that a developer has a new package or an improvement on an existing package, we need to deploy such software on the robot. So we have a script that we call pal deploy that basically allow us to reproduce the workspace on the robot. And this is done by copying the workspace on a folder, and thanks to the order in the ROS package path, we can overlay or we can add new packages to the system. But the important part of this method is that it's completely, let's say, can coexist with the installed Debian packages that we have in the system, and it's easy to roll back to a working system, just deleting the deployed workspace. And this also is done together with, let's say, a policy to avoid editing file on the robot, to avoid pushing before having validated the installation rule of a package. So through this tool, we can, in a convenient way, validate our software before pushing it to GitLab, for instance. Important constraint of the system that you need to respect API compatibility, because the development environment of the workstation should have the same version of libraries, or at least the same API of the robot, because otherwise you have two systems that are not consistent. We believe continuous integration is very important, and we use GitLab hooks together with Jenkins job, automatically triggered by pushes. And we build in clean environment. We add unit testing to our repos and coverage checks, and also API checks. And there are notifications for developers and maintainers in case of these errors appears. And the continuous integration is automatic for master and develop branch. We try to stick to the Git flow branching model for our software repos. And additionally, we have a way to visualize, let's say, the differences during merge request. So in this case, you can see that the merge request of the extended test branch into the master branch increase the coverage, increase the number of tests, and respect the API compatibility. So we have this graphical, let's say, way to help the user, the developer that has to perform a merge request, and understand what's going on after the merge request has been accepted. Also, we have a complex releasing system because we have more than 800 repos, so we can visualize the relationship between the software repos that we have in terms of dependencies and dependees, so that we can go on with the releasing process step by step, starting from the low-level dependencies and scaling up to the high-level repositories. And also, we have a remote way to upgrade the software that is delivered with our robots through a VPN connection, so that we can remotely connect to a customer facility to check the status of the robot, to provide the Debian upgrades or bug fixing. Now, I'm talking a little bit about the control architecture of our systems. We have several robots, as I already told you, but we try to use the same architecture so that we can reduce the effort of upgrading, adding new functionalities, or validating and testing our platforms. For this reason, I divided the system into three parts. We have, at the lower level, the hardware. We reuse hardware components. but there are always differences between robots. There are differences in communication bus. There are differences in sensors, in kinematic structure, and we try to abstract this thanks to ROS control. So ROS control is a component that is running in ROCOS, and in ROCOS we have another component that is the actuators manager, that is the guy talking to the hardware. And inside ROS control, we can load plugins. We can load controllers, already off-the-shelf controllers such as the joint trajectory controllers, the effort controllers, the diff drive controller, but also our own controllers that we developed following the same interface of ROS control. So we have the walking controller and the body controller. And then these expose everything, hardware, sensor, to the ROS ecosystem so that we can use navigation stack, move it, and all other libraries that are available in ROS. I want to stress the importance of using a real-time system when controlling robots, because hardware needs real-time communication, and also because the controllers need determinism. You want the robot to perform in a deterministic way. You want to control the timing execution of every controller, of every functionality, so you need to have a real-time system. Okay, what is the difference between the different robots? We try to stick to having just different URDF, different parameters in YAM file, and different launch file. So all our software is robot agnostic, and is configured with such parameters, or at runtime, parsing URDF, loading different plugins, and that's it. One of the controllers that are ROS control plugins is the whole body control. That is one of our most complex piece of software. And the philosophy behind the ROS control, the whole body control, is that we want to program the robot with high-level tasks. We don't want to go deep into kinematics, into joint control. So we want to define high-level tasks such as respect joint limits, avoid self-collision, put the end effector in that position, and at the same time we want some basic rules to be respected, such as balance, or keep the feet on the ground to prevent falling. And here I can show you some simulation of such system on different robots. So here we have RIMC and Atlas. With the interactive markers, we can move the end effectors. And here you can see the self-collision avoidance. So you have capsule around the links of the robot, and the robot is avoiding, is preventing to collide with itself, just because there is an online solver that is caring about this. At the same time, keeping the robot upright, keeping a reference posture, keeping the feet on the ground. And the whole body control is robot agnostic, as I told you. So it's configured through a URDF and through the specification of high-level tasks, such as center of mass position, gaze, go-to task for the end effectors, and joint limit task. This is translated into a stack of tasks in which the order is prioritized. And that translates to a mathematical problem, a hierarchical quadratic problem that is solved online on the robot at 200 Hz, for instance, in Tiago and RIMC, and at 1 kHz on Talos. Here is an example of a stack of tasks for a biped, for instance. So you have the high-level priority joint limits respect, self-collision avoidance, the feet on the ground, the center of mass centered in between the feet. And then at low priority, you have torso orientation upright. You want the robot to be straight if possible, and at joint reference posture. And this allows us to control the robot in a quite intuitive way, just by specifying simple end position for the end effector. So here you will see in the middle, the red dots are the position that should be reached by the end effectors, and on top you see a position that is where the robot should look. And all of this is solved online, so you don't care about joints, trajectories, or joint limits for avoiding the robot from falling. And we think that this is the future. So we need such kind of complex software that abstract the complexity of such platforms that have so many degrees of freedom that otherwise it's impossible to care with this complexity and developing a high-level application. Here is an example that will show you also how you can include forces with the environment into this framework. So the idea is that we have a force torque sensor in the right wrist, and the robot is following the force. So you can interact physically with the robot, and the robot will just follow the external perturbation, keeping the balance. You can see that the left arm is moved backward to compensate for the dynamics introduced by the person that is shaking the hand. And you can imagine this method being used also for manipulating a tool, for drilling, for keeping an object from the ground, for walking and resist perturbances. It's the same method. It's just a different task, different stack of tasks. We used extensively this method in the Space Robotic Challenge. You have seen yesterday the presentation from OSRF guys about the gazebo simulation for this challenge. So current and former Power Robotics employee created a team, the team Olympus Mons. Olympus Mons is the tallest mountain in the solar system. And we participated just for passion because we were ineligible for the prize, not being US citizens. And we arrived third. The challenge was complicated because the robot had to perform a lot of complex tasks of manipulation and walking in a simulated environment. But we managed, using the whole body control, to score well in most of the missions. And the result is that was fun, a lot of fun. It was hard because we spent really a lot of hours in front of our control station controlling this robot on Mars with delays in the communication, with limited bandwidth, integrating our whole body control with the whole body control provided by the organization through the IHMC whole body controller. But I think that was worth because we learned a lot, and also that all the software that we developed for this challenge is now already being used on our robots, thanks to the modularity of our software. So we have now a Talos robotic challenge, in which we will have Talos performing the same challenge that Valkyrie did on Gazebo. We have already this working after really 2 days of gluing together the component that we had already for the Space Robotic Challenge. I can show you also a video of the Talos going fast, picking objects, the briefcase, connecting the cable, and so on and so forth. And more important, now we will test this software on the real Talos. So we will make the real Talos challenge. Okay, so now in 2 months, there will be Humanoids Conference in Birmingham, and we hopefully will show some of these tasks on the real robot, thanks to the, let's say, the tools provided by ROS and the modularity of the software that we have developed on top of ROS. And I think that's it. So thanks to ROS community for all that is available outside, and thanks to you for the attention. And you can see a lot of RV simulation, RV visualization and gazebo simulation, but also a lot of Thiagos that we are delivering to happy roboticists. Thank you.
Thank you, Luca. We've got time for one quick question, if that's what you're headed for.
Hello, so you were talking about the whole body controller, and my question is if you can somehow plug in collisions with the environment, because to me it seemed quite simplistic and like a static design. But would that be possible to include more constraints to
more
the whole body
constraints? Yeah, sure, sure. You can add also environment constraints.
Yeah.
So you can add the table if you're manipulating as a constraint.
Yeah, and can that be done like during runtime, like from the sensors?
Yeah, I mean, maybe, yeah, I didn't tell you, but the pile, the stacks of tasks can be dynamically, so we have a pop and push functionality so that you can add task, remove task dynamically during runtime. So you can add whatever task you want as the sensor detect a plane or whatever. You can add that geometrical constraint that is going to be considered by the solver.
Okay, thank you.
Well, then let's thank our speakers once more.